All right, starting with our definition. So period, the capital T, is the time for one wave. Frequency, the lowercase f, is the number of waves per second, and your wavelength is the length of one wave. Transverse wave is when the oscillation is perpendicular to the motion. So let's say I have a wave going to the side, up and down would be perpendicular to that, so it would look something like this. The amplitude is the height of the wave, but it starts at equilibrium. So this right here is the amplitude, or equilibrium down would also be the amplitude. The wavelength could be from here to here. This is not to scale. Or it could be from crest to crest is a wavelength, or it could be from trough to trough is a wavelength. All of those work. This right here, these two are crests, and the bottom points are troughs. A student is sitting on the edge of a swimming pool, dipping their foot repeatedly, making waves that move. At first they dip slowly, so like something like this, and then they dip faster. So what you are increasing right there is the frequency, right? At first you only have like 1 wave per second. Now I'm sending 3 waves per second, etc. So your frequency is definitely increasing. Now period, so let's think about the relationship between those. So period is 1 over the frequency. So if I increase the frequency, your period should do the opposite thing. So that should decrease. Velocity, so the velocity of my hand, obviously my hand is moving faster, or foot, whatever it is, that's not what it's asking about. It's talking about the wave, right? So which of the following wave properties? The wave's velocity is staying the same because you're still in the same medium, right? Me dipping my foot faster does not make the wave travel faster across the water. And wavelength, so V equals F wavelength equation, we know that this is staying the same. We know the frequency is increasing. That means this one must decrease to balance out to the same, so your wavelength would decrease. How do these two sound different? So if you look, they actually have the same wavelength, right? Mark off 1. So they are equally as squished together. So they have the same frequency, which means they have the same pitch. The thing that's different about them is the amplitude. One of these waves has a much greater amplitude than the other. We're talking about a sound wave. Sound is talking about volume. So that means this one is loud and this one is quiet. And they have the same pitch because they have the same frequency, right? One is not more squished together. It just happens to be taller. Number 5, what type of wave? So here we're not getting compressions, we are getting crests and troughs. This is a transverse wave. The motion is up and down and the wave is going this way. See how that's perpendicular? Number 6, which of the following represents the motion as the pulse passes point P? So in this case, the wave is going to the right. What point P is going to do is it's going to go up and then come back down, and then it'll stay in the same spot. So for sure it's going up and down. Some people were choosing part D, or answer choice D in class. Think about point P is not going to move to the side, right? If you're thinking about like a stadium wave, when the stadium wave comes, you go up and you come back down. It creates this shape, but you do not move with it, right? It just moves, the energy moves to the side. So the actual motion is just straight up and down. How would these sound differently? So you'll notice they're the same height, so that means they'll have the same volume. This one is much more squished together, shorter wavelengths, higher frequency. So this one is a higher pitch. And this one is a lower pitch, but they have the same volume. How many wavelengths? So 1, 2, and a half. 2.5 waves. That is not the same as what is the wavelength. The wavelength is the length of one wave, which is 2. Different values. I want the amplitude to be greater. Amplitude would be like the volume, right? So I could just strike it harder. I'll have a greater like displacement movement. These two, when they meet, this is going to be a constructive interference. So you add together, this becomes 15. This is what they look like the instant that they meet. And then they'll, of course, pass through and continue. Period is the time for one wave. You have 4 waves in 10 seconds. So 10 seconds is not my period because that's not the time for one wave. That's the time for 4 waves. So if I want the time for just one wave, you take the 10 seconds, but I divide it by 4. And that would give me 2.5 seconds for each wave. Wave speed depends on the medium, so the only way to change the wave speed is to change the medium, change the material or substance that it's moving through, whether that's the slinky, air, water, etc. The wavelength is equal to A to G. No, that's a wave and a half. C to E, no, that's only half a wave. B to F, yes, crest to crest, that's a full wave. And D to F is only half of a wave, so no. Which of the following is half a wave? A to B, no, that's only 1/4 of a wave. C to E, yeah, that's only the bottom half, so that is half. B to F is a full wave, and D to G is a little bit more than a half, right? It's a half and a quarter, so it's like 3/4 of a wave. So, not these. This is a longitudinal wave, which you could have known just by the fact that you're getting compressions in spread out areas, not crests and troughs like this one. So it says what represents the motion of the particle at any position really, but it's talking about C. So which way is the individual particles moving to create this wave? So we know the wave is going to the right. When it's longitudinal, that means that the individual particles oscillate parallel to the wave motion. So if your wave motion is to the right, then the individual particles moving parallel, well, left and right is parallel. So that's C, number 4. The wavelength is equal to the distance between what 2 points? So very similar to a transverse wave where you just go from a crest to the next crest, right? The same point but on the next wave, or a trough to a trough, or equilibrium to equilibrium, etc. I'm going to go from one point to the same point just on the next wave. So here I don't have crests and troughs, but I have compression. So like these are my little compression areas. These are like my most spread out, etc. So A to B, those are not the same point, right? This is like just after a compression. This is like what's super spread out, not the same. A to C, yes that is. See how that's on the just after it's compressed and just after it's compressed. B to C, not a full wave. It's in the like almost to a compression and then right after, no. And B to E, close, but they're not the same position. This is in the middle of compression. This one is before the compression. So A to C makes sense. I have period, I have velocity, I'm looking for wavelength, so V equals F wavelength, velocity is 343. Looking for wavelength, frequency, I can find with period, so frequency is 1 over the period, which is 1 over 0.005, which is, what is that, 200? Yeah, 200, plug in your frequency is 200, divide over, you get V. 3 seconds to complete one cycle, so that means the time for one cycle, or the time for one period, or one wave, is 3, so that's my period, right? If it was the 3 seconds for 2 cycles, you'd have to divide, but it was just for 1, so that's my period. So frequency is just 1 over the period, so 1 over 3, which is 0.33 hertz. Right, here we are calculating the wavelength of each one first. So first I counted up how many waves there are. This is only half a wave. This is 1 wave. This is 1.5. This is 2 waves. Now the number of waves is not the wavelength, right? Wavelength is like how long the wave is. So wavelength for each of you, A, B, C, D. So B is super easy because I have 1 wave and its length, so the wavelength is 12 for B. For the rest of them, right, I have multiple waves or parts of a wave. So D, I like to think of this one. If you're confused on what to do, this is an easy one. I know that 2 waves takes up 12 meters, right, because it's still 12 meters. So then if I wanted just 1 wave, well, that's only 1 of these, so that would be 6 meters. What we did is we divided by the number of waves. So 12 meters divided by 2 gave me 6 meters. Here, for C, it's 12 meters, but it's only 1.5 waves, so divide by 1.5, that gives me 8 meters. Here, it's 12 meters, but I'm dividing by 0.5, and that gives me 24 meters, which is okay that it's longer, because if this is only half a wave, a full wave would be longer. So I've got 24, 12, 8, and 6, and the wavelength, of course, is getting smaller as we go down, because look, they're getting squished in. Highest pitch. Pitch has to do with frequency. The one that has the highest frequency would be D. More squished together, shorter wavelengths. The speed of D is 48. What would the frequency be? So V equals F wavelength. 48 equals, looking for frequency. The wavelength for D was 6. So that gives me a frequency of 8 hertz. What would the frequency of A be? So V equals F wavelength. My frequency is definitely changing because my wavelength is changing. The wavelength for A is 24, but my speed should be staying the same. the same like medium, right? It's the same strings. So 48, and that gives me a frequency of 2 hertz. Same idea for these, I'm just using B and C as values. So 48 is same velocity, looking for frequency. Wavelength for B is 12. So for B, the frequency is 4. And 48 still. Wavelength for C was 8, so frequency for C is 6 hertz. So I had a frequency of 2, then 4, then 6, then 8. So you'll notice there are multiples. This, I'm getting crests and troughs, not compressions. That's a transverse wave. If the frequency is 5, what is the speed? So V equals F wavelength. Frequency is 5, just looking for wavelength here. So from here to here is 15. So that is not my wavelength because that's more than one wave. So 1.5, so 15 meters divided by 1.5 waves gives me a wavelength of just 10 meters from here to here. That makes sense. So that gives me a velocity of 50 meters per second. Highest frequency to lowest frequency. Highest frequency is the most squished together, so that's definitely B. The lowest frequency is the most spread out, so that's a D. So notice in the same distance I only have 3 waves, so D. And then I've got the same amount of waves, so I think A and C are like equally as squished. Largest wavelength to smallest wavelength. So largest wavelength is like literally length, longest length. So this is a longer wavelength. This one is a longer wavelength, D. A and C look about equal. And then B is for sure the shortest wavelength. Now period, so frequency is 1 over the period, well I guess I'll do the period is 1 over frequency. So my largest period comes with the smallest frequency, and my smallest period comes with the largest frequency, so I'm just going to reverse the order of the frequency, they're opposites. And fastest to slowest would be the same speed because I'm assuming they're all in the same medium. Alright, how would I hear the change in the sound waves below? So I noticed that the amplitude or the height of the wave is staying the same, so it's staying the same volume, right? If it's loud, it's staying loud. But I do notice they're getting more squished together, so you're going from low pitch to higher pitched. Now here, my amplitude is changing. I'm going from loud to quieter. Because my amplitude is decreasing and I'm keeping the same like wavelength, same squishedness, so same frequency, same pitch. So your wavelength is increasing, what happens to everything else basically? So wavelength is increasing, amplitude must also have changed. No, your amplitude, right, is like absolutely separate from everything else, so no. Your frequency and speed, so we know that speed is staying the same, so now I'm just going to look at my equation. Speed stays the same, frequency increases, your wavelength increases, which means your frequency must have decreased. The only way these balance out, so frequency does the opposite, decrease. Which of the ones here is loudest, so loudness has to do with the amplitude, so the most amplitude, which is A. Quiet, again, amplitude, I just want the least amplitude, so least amplitude would be either B or either C or D, it's kind of hard to tell between those two. Highest pitch is the highest frequency, so most squished together, that's for sure D. Lowest pitch is the least frequency, so least squished together, most spread out, so that's B. And the one that's high pitched and quiet, it's squished together and not tall, so D is squished together and also quiet, not tall. If you have a shorter wavelength, so if wavelength decreases, your frequency is going to increase for the same reasoning we talked about right here. Frequency increases, that is going to sound like a higher pitch. It does not tell me anything about loud or quiet, just that my frequency is increasing, so it's a higher pitch. Frequency is the number of waves per second. So a couple ways to do this, but I just went to 1 second. I said, okay. From 0 to 1, and then 1 second, I get 2 waves. So I have 2 waves per second, so my frequency is 2. Other way is to look and say, okay, my period is 0.5, and frequency is just 1 over the period, which is also 2. Some people did number of waves per second, so 1, 2, 3, 4 waves in 2 seconds. 4 over 2 gives me 2. So multiple ways of thinking through it. 2 waves are traveling through the same container of nitrogen gas. Wavelength A, wavelength B, the speed is the same because it's the same medium they're traveling through. What must be true about the frequency? So V equals F wavelength. So wave B has a greater wavelength, so that must mean it has a lower frequency. So it has a lower frequency because it has a longer wavelength with the same speed V. We're using this diagram here. If my period is 0.5, that's capital T. What is the speed? So speed is V equals F wavelength. Frequency is 1 over the period, which is 1 over 0.5, which is 2. Now wavelength, I have 6 meters here, but that's not the length of one wave. That's the length of 1, 2, 3 waves. So then one wave would be 6 meters over 3 waves, so one wave is just 2 meters. Plugging in wavelength is 2, you get a velocity of 4. Amplitude is the height. Remember, we measured amplitude from equilibrium, so equilibrium up is an amplitude of 0.2 meters. Here I want to know what point P is doing. So this is a transverse wave. The wave is moving to the side, but the actual motion of the cork or the point, whatever, will be going up and down. So we can cross off C and D. And now it's just which do I do first. So what I'm going to do is I'm going to take this wave and I'm going to shift it over to the left a little bit. So shift over. And then you'll notice point P is going to be below where it was before, so it must have moved down first. Frequency is 40. What is the velocity of the wave? So V equals F wavelength. Frequency is 40. Now I just need to find wavelength. So 3 meters is from here to here. 1, 2 waves. So then 3 meters, that's for 2 waves, gives me 1.5 meters for just 1 wave. That gives me a velocity of 60 meters per second. High pitched, pitch has to do with frequency, which means you have a big frequency. Period does the opposite, so period is 1 over frequency, so high frequency means small period. And V equals F wavelength. V is staying the same, so if I have a high frequency, this would decrease, so short wavelength. So I want big frequency and small period or wavelength, so C. The amplitude is unaffected, right? High pitch tells me nothing about loud or quiet. That's a separate category. Here, this entire thing is 7 meters long. This is 1.5 waves. So if I want the wavelength, the length of just one, you just take the centimeters, divide by 1.5. That gives me 4.67 meters. The harmonic, just look at how many loops I have. I have 1, 2, 3 loops. This is the third harmonic. What would the wavelength of the first harmonic be if it were to travel through the same string? So same string means the string is still 7 meters, right? But first harmonic means only 1 loop, so that's only half a wave. So 7 meters divided by half gives me a wavelength of 14 meters, which makes sense. If this is 7, then a full wave would be 14. The frequency in the first harmonic is 10. What is the frequency in this shown harmonic, so above? So I'm going to use V equals F wavelength. Frequency is 10. I have to use the wavelength that goes with that, which is the first harmonic. The wavelength in the first harmonic is 14. Gives me a velocity of 140. And now I can use 140 with my third harmonic's wavelength because my speed stays the same. So it's still 140. You just divide over, you get a frequency of 30 hertz. And then speed we already found was 140. And lastly, the challenge. So the pipe is 0.7 meters. I have frequency, what's the speed? So V equals F wavelength. Frequency is 120. I need to find the wavelength. So this is 1. And then this is only half of a half, right? Because a loop is half a wave. This is half of a half, which is a quarter. So this is like 1.25 waves. So I'm going to take the 0.7 meters and divide by 1.25. That's going to give me a wavelength of 0.56. And then we can plug in, get a speed of 67.2.